Sir, Shri A.K. Bajaj is the former chairman of Central Water Commission. He has a very vast experience in the water resource sector, especially in dam safety aspects, gate designs, etc. He is currently actively engaged as the chairman and members of Dam Safety Review Panel. Sir, I extend you a very warm welcome and I would request you to kindly be seated on the panel, please. As the co-chairman of the session, we have with us Mr. Daniel Johnson, Principal Expert AECOM, Colorado, USA. So welcome to the panel. Mr. Johnson is currently working as a Principal Dam and Hydropower Engineer associated with AECOM, one of the leading consulting engineering firms in the world. Mr. Johnson has an extensive experience over 40 years in water resources, dam engineering, geotechnical engineering, and civil engineering. He has been deeply involved as a project manager or technical lead on about 220 water resource and mine tailings dam projects in the US, Canada, Africa, Asia, Australia, New Zealand, Afghanistan, Sri Lanka, and Central and South America. His roles have covered all project components from planning, evaluation, design, bidding, construction, and operations. So welcome to the panel. And I would now also invite on stage our rapporteur for the session, Shri M. Ramesh Kumar, Director, Central Water Commission, India. And I would request if you can give a round of applause and welcome our panelists to the session. Thank you very much. I would now request the chairman for the session to give the opening remarks, please.
Good afternoon, everybody. As you would have read before coming here, this session is basically on dam safety rehabilitation actual projects that have been done, and case studies are going to be presented. We have 5 speakers with us today and a time limit of about 1.5 hours. So we'll be giving 15 minutes to each of the speakers, and the last 15 minutes we will have questions and answers at the end, rather than disturbing the flow of the presentation. So without much ado, we'll start. Our first speaker is Mr. Daniel Johnson. The lady has just introduced him. He's my co-chairman here. He will be giving the first paper. That's the theme paper to start the session. It's on river management for dam rehabilitation projects. Mr. Daniel.
Thank you. Okay. Thank you and good afternoon. Thank you, Mr. Chairman, for the introduction and also our hostess. I'm pleased to be here at the conference this all week. It's been a very enlightening conference for me to come to India from Colorado, USA, and spend some time here and understand the issues with dam rehabilitation. I've been involved in many of the projects in the U.S. that we've been going through over the last 30 years on rehabilitation of dams, and I find those to be an incredibly interesting approach to a career for engineering. What I'm going to talk about this afternoon is ties a bit in with risk assessment. What we find is that in many areas we talk about risk assessment this morning and yesterday regarding project survival and sustainability, but also during construction there's risk. And so I'm going to talk a bit about one aspect of risk in construction that engineers need to know about and owners should understand as well. So I want to thank right off the bat my co-chairman, which is our co-author, Ken Hansen. Ken's a friend of mine, but Ken was with the Portland Cement Association for many years and helped develop a lot of the technologies in soil cement and roller compacted concrete. Let's see. Which button does it? This button. Nope, that's the light. That's what I thought. That's what I'll just do. Yes. I can just do it. Anyway, thank you. One thing we find in dam rehabilitation projects, there are many different types of construction aspects that are required. Every dam that needs rehabilitated has other components or special components that need to be taken care of. And so there's many types of construction. And some of the construction activities are upstream, some are downstream, some are on the crest, outlet works, spillway, a lot of different parts of the dam. A lot of the work is with outlet works and upstream sides. And so what is to be done with the water in the reservoir? And how to manage the water that's in the reservoir during construction. And so that's the aspect to get into is we've got dewatering the reservoir during construction, keeping the stream flow out of the construction area during construction so the construction can go in the dry. The goal of that is that how do we retain operation of the reservoir during construction? And in many cases we've developed new technologies with remote control, underwater construction that enables us to leave the reservoir in place. But in most cases we actually unwater the reservoir to get the work completed. And one thing I find that's very interesting in dam rehabilitation is that the reservoir level requirements vary through the period of construction. And I'll show how that kind of fits within it. But the whole idea is that we keep the stream flow away from areas of construction that would be infected by that stream flow. Typically we look at cofferdams. That's what the basic topic is today, is cofferdams and how we manage those. But in almost all new dam construction and in many rehabilitation projects, cofferdams are implemented. They can have failure mechanisms associated with them that cause problems on construction. And what I find is that a great number of cofferdams, it's between like 30 and 40 or maybe even 50% of cofferdams have problems during construction of rehabilitation of projects. So it's an issue to be considered because every time a cofferdam overtops, there is some impact that exists. Cofferdams are temporary. They're put in place for construction expediency. And so there's a cost to build them, maintain them, and then take them out that in most cases wants to be minimized. But that cost needs to be balanced with the consequence should they fail or not perform correctly. This is just a graphic showing an outlet works, new outlet works construction on an embankment dam. This shows the cofferdam on the upstream side with the reservoir in the back. This cofferdam is an embankment material. This is the new outlet works construction. There's a conduit beneath the dam in this location. This cofferdam was put in place through water and then sealed by using the materials that were on site. Of course, they tend to leak a little bit, so in this case there's a pump that allows the water to be pumped out of the excavation and keep the excavation dry. Another example of a cofferdam. This is actually on a new dam, but the cofferdam is built upstream, the reservoir is retained behind it, and the stream is routed around through the operating tunnel outlet works. That allows the dam to be constructed in the dry, including the upstream area, and this cofferdam in place is for the life of that construction in this case. There's a responsibility that needs to be defined fairly early in the process, and there are a couple different schools of thought relative to who's responsible. In many cases, and this is in the US and I think in some other countries, is that the contractor tends to take responsibility for the cofferdam, and the reason being is it's a construction method, and usually the contractors are responsible for construction methods. So they tend to take responsibility. However, I see internationally and actually in the US right now, we're starting to change that because cofferdam failures have become a cost and a time schedule impact. And so we're looking at the idea now that we can use a contractor designed or an engineer designed, and usually the owner is responsible for making that decision. Ultimately, the owner bears responsibility because it's his project or her project. And what we find now in the United States is that dam safety regulatory agencies consider that a cofferdam is a physical water retaining structure, and so they actually review and approve the designs for cofferdams. They also consider that if a cofferdam is large enough, it may retain a large body of water that, should that fail, it may affect the downstream landowners, population. So there's an impact of physical damage and life loss potential downstream. And so they get into it and actually can, in some cases, look at what is the hazard classification for a cofferdam. So it's become much more complicated from a standpoint of getting a cofferdam design, built, and operating. And right up front, it's very important to have a clear understanding of who has responsibility for what. And two of the major aspects that I see are, one is the minimum capacity that the cofferdam is responsible to maintain or required to pass. The second is, should it overtop, what kind of resistance is built into the system so the cofferdam itself doesn't fail. Cofferdam design historically looks at frequency of floods. And historically there was a concept that basically it was the flood that was pretty much 5 times the exposure period. If it's a 2-year construction project, the design flood selected to be the 10-year flood. If it's a 5-year project, the design flood would be a 25-year flood, etc. That concept is falling away a bit towards a risk-based approach. And the risk-based approach, looking at what the flood recurrence interval is tied to tolerable risk. And we've talked about tolerable risk through the conference here the last couple of days. That's looking at what is the window where this cofferdam is supposed to perform. It may be 6 months, maybe 4 years. The window that's exposed, the likelihood that a flood of a certain size may occur during that window, and then the consequence. What happens if the flood occurs and the cofferdam fails? So all those go into the risk assessment. And the owner, along with the contractor and usually the engineer, and in the United States, the regulator, make an agreement of what that should be. There's also a type of construction. There are many types of construction. I'll go over in a little bit here. And the construction schedule. I'll show a graphic here, but we don't have the same flood recurrence intervals every month of the year in many locations in the world. Here we have the monsoon season and the dry season. And then also the construction activities that are impacted. Should a flood occur and a cofferdam fail, what is the impact to the construction? Is this one better?
Yes.
Okay. Thank you. And so the idea of how that all fits together ties into how the cofferdam is designed and operated. Well, theoretically, that one works better, but we'll try this one. Actually, I'll just forget that and go with this. This is just a graphic and shows what I was talking about with relative floods. That in this case, the graphic at the bottom, this is, nothing works on that one. That didn't work either. Oh well. Anyway, what it's showing about along the bottom are the months of the year. So this is a 12-month season. And at this location, which is in the Rocky Mountains of Colorado, is that during the wintertime, January, February, and then at the other side, November, December, the floods are quite small. And if you take a look at the high peak, the top bar on that is the 50-year flood. The first dashed line is 25-year flood, 10-year flood, 5-year flood, etc. And you can see that depending on the month of the year that you're trying to protect the construction, you look at a different flood condition. So that's a very important aspect to look at. That kind of a concept can also affect the construction sequence. So a lot of contractors will look at this kind of a graphic and select how they're going to build a particular component, maybe when there isn't a good chance for a flood. As I mentioned, there are many different types of materials that cofferdams can be built out of. Probably the most common is rock fill. You can place rock fill in water. It still has strength. It has permeability, but you can do something to the rock fill, including pump out the excavation to remove the water that seeps in. Zone rock fills are common as well. In many cases, the rock fill downstream zone will be placed in the river or the reservoir. Upstream of that would place soil, and maybe upstream of that a membrane or something that would go in place. Also, sheet pile can be used. A rock fill embankment can be constructed, and sheet pile can be driven through the crest of that, providing seepage mitigation. Soil can be placed, and the first two graphics showed soil embankment cofferdams. And in that case, the soil can be placed with just the soil. There's membranes that can be placed on it, whether the membrane is a geomembrane or some other type of membrane, and again, sheet pile. Embankments typically need some sort of erosion protection to keep them from eroding away, both during operation with wave action on the upstream side and also with the potential for overtopping. And so a lot of different types of embankment protection systems have been used. Interlocking blocks, different type of revetments, placed concrete slabs, a variety of type of things can be placed for erosion protection. And then cast in place concrete can be used. Many cofferdams are just a vertical concrete wall that may be, for a small project, maybe 3 or 4 meters high. Works very effectively. And then in many cases, there'll be, for a small project, portable structures. There are a variety of portable structures, some made out of structural components, others made out of bladders like rubber dams that can be placed in the river to close off the river. We'll talk a bit about roller compacted concrete, which is RCC. That's the fairly new technology of placing concrete. And we're finding that RCC is a fairly inexpensive approach for cofferdam construction and enables overtopping with no or little damage. This is just a photograph of an embankment cofferdam that didn't survive a flood. And so you can see in this case that the river has breached the cofferdam on both sides. The flow is going across the foundation area for the dam. This is a similar photograph where a cofferdam again is overtopped, but the cofferdam is made of roller compacted concrete, and albeit there is water flowing through the construction site, at least the cofferdam is in place, and repair of the systems will take a lot less time. This is just a graphic of construction of a roller compacted concrete cofferdam. This is actually a downstream cofferdam on a dam, so you keep the downstream tailwater excuse me, away. But the placement of RCC, which we've seen, is just a dry concrete placement. It's very effective for that. And this is just a graphic then of a roller compacted concrete. I will. Dam, this is one that was constructed, this is about 20 years ago in Canada. This is one actually that replaced a failed cofferdam. The photo on the left, you can see where a cofferdam that was an embankment cofferdam failed. And then if you look in the right photograph, it's replaced at this location. If you notice, this face and this face are the same faces, but this then they placed a roller compacted concrete cofferdam in the place of the one that had eroded out before. So, to summarize, we have to deal with cofferdams or some kind of river management system during many dam rehabilitation projects. I think that risk-based approach to that selection of a cofferdam is the most appropriate approach, and to see that looking at what are the consequences, what are the likelihood of conditions resulting in a failure, and then who's responsible for this, and then what are the risk tolerances for those responsible persons. What I've seen is many times historically that dam constructors are likely to take more risk than a dam owner or a dam engineer, so that has to be weighed. Length of construction activity. How large is the window of opportunity for a flood condition to exist? And then the final point that I'm saying is that RCC seems to be a good alternative for construction of a cofferdam material, just because it has strong resistance, fairly easy to construct, and fairly inexpensive. So, thank you.
Thank you, Mr. Johnson. Our next speaker is Professor Mudgil from the Water Resources Department of the Anna University. in Chennai. He'll be talking about the dam break analysis modeling that he had done for Sothupurai Dam in, I think, Tamil Nadu again, and using the various softwares like Astrodam, ArcGIS, HES, HMS, and HECRAS. So, Professor Mudgil.
Yeah, good afternoon, everybody. I thank the chair and co-chair and the rapporteur and the organizers of the conference for providing me this opportunity to present some of the work which we have done in dam break analysis and flood mapping for Sothupurai Dam. So this work was mainly done by Kabir Ahmed, who is not here, and Balamurgan, who is here with me. And this Sothupurai Dam belongs to Water Resources Department, and it is one of the drip dams for which this EAP has to be prepared. So before we prepare the EAP, this dam break analysis and flood inundation mapping is important. How do I move to the next slide? No, here I'm getting the next slide, but it's not moving there. No, laptop key also it's.
Cable had been unplugged. It came?
Cable problem. This is yours? No, not this one. I'll use the keys directly. I'll use the keys. Sorry for the hitch. So we all know that dam break is an important component of flood inundation studies. It involves arriving at the design flood using the probable maximum precipitation. Now this dam is built across Varaha Nadi in Tamil Nadu, and it is the second highest dam in Tamil Nadu. It's about 10 kilometers away from the Periyakulam town, and the catchment consists of a number of small streams from Kodaikanal Hills and the release of water from Berijam Lake. And Varaha Nadi runs for about 35 kilometers downstream before draining into Vaigai River. So we have the map of, yeah, here we have the map, and this is the Sothupurai Dam, and we have a habitation here, Periyakulam, which is about 10 kilometers from Sothupurai Dam, and finally this Varaha Nadi confluences with Vaigai Dam, Vaigai River, about 35 kilometers from Sothupurai Dam. Now this is the methodology that we adopted. First we create the dam, then collect the rainfall data, then arrive at probable maximum precipitation, and we use the hydrologic model HEC-HMS, for which we use both the pre and post processing using GeoHMS. Then the results of this is routed through HECRAS, and then the channel routing is done and unsteady flow analysis is done. Then we have the output results, and again use the GeoRAS for post-processing, and then prepare the flood inundation maps. So the salient features of this dam are the catchment is quite small, like about 48.64 kilometers square, and then the full storage capacity is 2.8 million meter cube. The top level of the dam and other details are given. So the important things are here, the catchment area and then the maximum discharge, so which is about 800 meter cube per second. Now we use this rainfall frequency analysis, and the daily maximum rainfall for every year was identified from a series of data for about 38 years, which was obtained from Department of Statistics. And frequency analysis was done using Weibull's formula. And then the goodness of fit revealed that Gumbel distribution would be a good fit. So we have the result for this frequency analysis. Then there are two methods of arriving at the probable maximum precipitation. One is the physical method. What we have used here is the widely adopted Hirschfeld method, which is a statistical method, and the expression is xn bar plus km sigma n, where km is determined by this xm minus xn minus 1 bar over sigma n minus 1. And the result of this km calculated is about 4.66, and the PMP that we obtained is about 434 millimeters. And since the area of the catchment is less than 50 kilometers square, we use a rational formula to determine the peak discharge. And the coefficient C, runoff coefficient, is calculated from the land use cover map, which is again obtained from the Central Groundwater Board. And time of concentration is determined using the Kirpich formula. And the results for C is about 0.83. And the time of concentration is about 0.95 hours. And here we find that the peak flood that we get is about 1789 cumex, which roughly corresponds to a return period of about 135 years. Although when we talk about probable maximum flood, we generally don't associate a return period, but then we just checked that this roughly corresponds to a return period of about 135 years. Now this is the input to the HEC HMS, where we have divided the basin into sub-basins and things like that. Skip this. And we did the HEC HMS analysis, and then we almost got the same type of results, like about 1800 meter cube per second is the peak discharge. Now for the dam breach analysis, various dam parameters, dam breach parameters like the breach depth, breach width, and breach side slope and breach formation time are required. And we use the guidelines given by the Central Water Commission, and then the failure time is to be in the range of about 0.1 to 0.5 hours. And the breach height is taken to be 57 meters, which is also the height of the dam. And the breach width was found out using the Froelich equation, and it works out to about 35.35 meters. And then the formation time was assumed to be about 0.167 hours, that is about 10 minutes, because the range is to be between 0.1 and 0.5. So we chose 0.167. And these are the results. For example, we have the RAS modeling screen output. Here we have the dam, and then this is the assumed breach. Now the results are that the flood inundation maps were prepared for 3 return periods, that is 50 year, 100 year, and then the 135 years, which corresponds to the PMP value. The maximum depth of water was about 43 meters when PMP was considered, and for 50 years and 100 years it was about 40.7 and 42.3 meters. And these were the depths which were just downstream of the dam. And then the maximum velocities were determined to be about 800 meters downstream of the dam, with the velocities being about 11.41 meters per second to 12.2 meters, which corresponds to 50 year and 135 years, or the PMP. Now, the water depth for a length of about 10 kilometers downstream, which is the forest area, is generally greater than 10 meters. Why we took this 10 kilometers is that the Periakulam town is 10 kilometers downstream of the Sotuparai Dam. And the river in some places runs parallel to the highway, where the depth is generally found to be in the range of about 3 to 7 meters. And the depth of inundation is 1 to 5 meters in Melmangalam and Sotuparai, with croplands and residential areas likely to be inundated. And these are the maps for the depth profile of Varaha Nadi for the PMP. So here we have the depths in meters, and we have the flow velocities. Like the maximum flow velocity is about 11.5 meters per second, and this 43 meters is the depth immediately downstream of the dam. Okay, so these are some of the references, and thank you for your patience listening. Thank you.
Thank you, Professor Mudgil. Our next speaker is Ms. Sarita. She is a project engineer with the company, both Kaushi Power Company Private Limited, having 10 years of experience in hydropower development.
Yes.
And
This is for the next day.
she'll be giving us details of the case study on rehabilitation of a dam in Nepal. I didn't find the paper in this compilation, so I'm not able to tell you what is there, but I think she'll give you the details.
Thank you, Chairman.
Ms. Sarita.
Good afternoon and namaste to everyone. Our paper topic is dam safety and rehabilitation in Nepal, need, opportunities, and case studies. Primarily, I will be focused in the case study part of my project, Upper Bhotekosi Hydroelectric Project, which had suffered 3 consecutive natural disasters. Its impact in the project and the rehabilitation effort we have made till present date. And then I will conclude with the state of affairs and the need and opportunities in Nepal. So starting with the project information, this is the project layout of my project in the artistic view. We have concrete dam of 60-meter long concrete dam, and we have 2 spillways and 2 side intakes, 1 surface descending basin, and waterway consists of 3.3 kilometer tunnel, 370-meter penstock pipe, surface powerhouse, and we have 2 bay 132 kV substation and 25 kilometer long transmission line. As I said that we have suffered 3 consecutive natural disasters. Starting with the first disaster, it was a Jure landslide. On the second day of August 2014, around 2:36 a.m., there was a huge landslide which formed a temporary landslide dam in the Sunkosi River, forming 50-meter height temporary dam and impounded the Sunkosi River. Though this landslide was far downstream of our project, but our project had to take outage because 4 of our transmission towers were directly impacted by this disaster. And after doing the temporary realignment through the left bank of the river, we came in operation after 172 days, 72 days around early 2015. And we did the permanent alignment through the right bank of the Sunkosi River after traversing this landslide. So this is the picture of the Jure landslide. So you can see that this whole mountain collapsed and formed the temporary landslide dam in this river. And this tower 61 and 62 was directly in this landslide, and tower 59 and tower 60 was impounded when when the lake was formed. So after coming in operation for a few months of early 2015, we encountered another disaster. As you know, it was a well-known earthquake of Nepal, Gorkha earthquake. On April 25, 2015, there was a huge earthquake event in Nepal. Though this earthquake event of 25 April itself did not cause major impact in our structures, and the personals were safely evacuated in the safe places. But however, there was subsequent huge aftershock, and which caused the major rockfalls from the uphill of the penstock, which hit one of the penstock, and it eventually ruptured, and all the water that was stored in the tunnel was flooded. This flooding, which caused the flooding of the powerhouse and severe damage to the camps and infrastructure. However, we were fortunate enough that no serious injuries and the fatalities at the personnel at the site due to this event. This is the picture of the penstock after it got ruptured and the tunnel water was fully flooded, and this is the water just that drained from the tunnel. This is the aftermath of the earthquake. This is our powerhouse, which was fully flooded, and the debris in this transformer area. This is the turbine floor, which was flooded and all deposit with sediments. And this is the generator floor after we did dewatering. So immediate assessment was not possible because of major aftershocks after this earthquake, and we did the assessment, and we set some after doing the detailed assessment by our consultant from Stantec, we started the rehabilitation of the project in early September 2015, and the major works were the replacement of the penstock that were damaged by the earthquake. And in this time we have considered this penstock ridge to be encased with the concrete, and then we later fill with the earth material. And we also considered to install the rockfall protection system in the uphill of the penstock, which was designed and which was to be designed by Trumer, Austria. And in the powerhouse area, refurbishments of the units by the replacement of generator core and windings, and replacement of all electrical equipments inside the powerhouse, and recovery of mechanical equipment and parts. And also we have to construct new tail-race outlet box culvert. From this earthquake event, there was many landslides in the catchment. So there was a huge sedimentation in the river. So riverbed got elevated. So we had to consider this tail-race box outlet culvert to meet the riverbed level. By July 5, 2015, we had almost completed 80% of our rehabilitation work, and we are about to commission first unit by December 2016. But all our this rehabilitation work went in a van in a single evening. Now we had encountered another disaster, which was Glacier Lake outburst flood. On July 5, 2016, during evening time, there was a massive flood in the river. Let me share you my own experience in this case, because during rehabilitation work after the earthquake, I was deputed in the project site. So when this flood event happened, I was at the project site. So I myself witnessed this glove event. So on that evening, we felt some ground shaking in the beginning, and we thought that it was an aftershock of the earthquake, because at that time also we were having some aftershocks. But later on, we could hear the big noise of the boulder collision in the river, and also pungent smell of the debris. So it indicated that there was a big flood in the river, and the nature of the flood indicated that it should be some kind of outburst flood. But the lack of communication with Chinese part, the cause of the flood was still confusing. So, and because of the transboundary issues also, it was not possible to immediately investigate in the cause of the flood. Later we ourselves engaged Chinese Institute of Mountain Hazard and Environment, Chinese Academy of Science, based on the Chengdu, to do the detailed investigation and determine the root cause of the flood. And from their investigation, they determined that we determined that the Gulf was from Gongbatong Sakuo Lake in the Zhangjiangbo Valley in the Tibet, China. And from their investigation, they estimated that the peak discharge in the headworks was 2,576 meter cube second, and the powerhouse was 2,098 meter cube per second. During earthquake event, there was no single damage in the headworks area, but from this Gulf event, our headworks was damaged subsequently with the failure of descender basing riverside wall, undermining of the dam, breach of right bank abutment, damage to the spillway gates and other hydromechanical equipments and the powerhouse and the controllers. Powerhouse was again flooded with the damage of the all newly installed electrical equipment inside the powerhouse. Also the equipment that were procured and stored in the storage facilities. This is the picture after the Gulf. This is during our operation. As you can see, all these headworks is covered with these boulders and debris. And you can see this descender basin right riverside wall was all collapsed. And you see this one part of the descender basin wall is in this side. So this was literally blown out to the other side. So you can imagine the force of that flood. And this descender basin wall is 2 meters in width, 16 meters in height, and it is about 60 meters in length. Sorry. This is a picture taken during monsoon season. Eventually, the river breached the right abutment of the dam, and it started flowing through the right bank of the river. This is the picture. The powerhouse was again flooded. This is the control room. The electrical equipment that were installed in the powerhouse were all damaged, and all the newly procured electrical equipment that were stored in these storage facilities were all damaged. And this is the turbine floor. And this time the debris was much more than from the earthquake event, because it was all about like 1.5 meters in height. As I said that we engaged Chinese Academy of Science for the detailed investigation of the Gulf. They did some investigation through satellite image as well as field investigation. And this is the satellite image of the area before it got. This is the tiny glacier lake that burst. Actually, it's about 132,000 meter cube in volume, and this lake is much more bigger than this lake. This is about 140 times bigger than this lake, and this was burst in 1982. And this is the picture after it got burst. They did some field investigation also, and this is the mouth of Glacier Lake outburst, and this is the lake itself after it got fully drained. So we started again reconstruction work based on the EPC approach. Our contractor is Sino Hydro Corporation Limited, China, and our owners engineers are from Stantec, United States of America. So major scope of work at the dams are, of course, starting with cleaning of all those debris and reconstruction and rehabilitation of all the damaged structure in the headworks, and reconstruction of right bank abutment and restoration of slope protection works, and restoration of highway there, and replacement and refurbishment of various gates, hydraulic equipments, and electrical equipment. And at powerhouse site was replacement of the damaged penstock Ridge 1, Ridge 2, and Ridge 3. And this time we have also considered Ridge 3 to be encased with concrete and then filled with earthen material. And refurbishment of generator, turbine, and mechanical equipment, replacement of 2 main power transformers, replacement of almost all electrical equipment in the powerhouse once again, and installation of permanent bulkhead at the powerhouse main door, and replacement of switchwire equipment. Immediate protection measures were taken in order to prevent our powerhouse from further flooding. We heightened the powerhouse by 2 meters after doing the hydraulic analysis in the area, and all the openings in the powerhouse were plugged with the concrete. And also this is the continuation after the earthquake rehabilitation, installation of rockfall protection system in the uphill of the penstock area, which was designed and installed by Trumer, Austria. This is the reconstruction work started in the head oaks area. Boulder breaking and the debris clearing was one of the challenging job there. And this boulder itself, this is the biggest boulder we encountered. It was about 17 meters in dia, and for particular this boulder, it took about 1.5 months to break and clean from that area. This is the picture during phase 1 Kafar Dam. This was taken during last monsoon. We have already cleaned this area also. This is the phase 1 Kafar Dam. Now we have already completed the construction of this descending basin riverside wall. Also repair works in the spillway, OGs, stealing basin, aprons. And we have started diverting through the spillway now. We have already constructed these 2 piers, deflector walls here. This is the overview of phase 2 Kafar Dam. Now we have already diverted water through the spillway, and now we are focused in the construction in this area. As I said, the penstock is being encased by the concrete, and then later we will fill with earth material. And after passing all the tests, generator have been already, it is confirmed that generator is recovered, and generator I have already assembled, and this is the tail-rest outless box culvert construction. This is the, we are still progressing well in our, in this area. And our construction is going well, and we are expecting to commission our first unit by early October 2019. And this is the specific case of Upper Bhotekosi hydroelectric project in our country. But I would say that this is the lesson learned to everyone, and we need to establish proper disaster risk management system and proper asset management system in our country. Now moving on to the general part, being said that Nepal is very rich in water resources, we are mainly focused in hydropower only. But it could be the multi-purpose like irrigation and recreation and transportation. And as a need and opportunity, my co-author Dr. Sanjay Giri have recently approached this model in Nepal, and we have also recently entered into federal government system, and this could be the good approach for Nepal, in which dam safety and management could be the part of river basin authority. Also, we need the proper institutionalization of dam safety and management as a part of participatory river basin management in Nepal. Also, as I said, we have recently entered into federal government system. This system can be exploited as an opportunity to adapt the process. Also, as a non-structural components and prerequisite, we could strengthen and enhance institutions and authorities, and also establish new primary and secondary authorities like River Basin Authority, institution, and knowledge bank. Also, we could adapt new and innovative methods and technologies, as well as a capacity building and development of skilled professionals in the country. With this message and the real case study, I would like to conclude my presentation. Thank you.
Thank you, Ms. Sarita. Our next presentation is by Shri M.R. Bhajantri. He is an officer from the Central Water and Power Research Station, which is located in Pune, India. It is one of the premier organizations in the country that is doing physical modeling as well as computer modeling for various project components. And he will be making a presentation on the hydraulic model studies done for the design of the additional spillway of Hirakud Dam. Mr. Bhajantri.
Okay. Respected dignitaries on the dais and fellow delegates, now I am presenting a presentation on hydraulic model studies for the optimum design of additional spillway of Hirakud Dam, Odisha. The studies have been funded by DRAPE, provided to Hirakud Dam Authority. The Hirakud, this is the satellite imagery of the Hirakud Dam and reservoir. This is the main dam of 4.8 kilometer, and there is a dike plugging the low saddles on either side. This is the left dike and this is the right dike. The length of the dike, including main dam of 4.8 kilometer, is 25.8 kilometer, and the total area of the reservoir is 743 square kilometer. So this is the main dam, and at the dam site there is an island. It was existing even before construction. There was a branching of Mahanadi river just downstream of the main dam. This is the left bank spillway. Based on the topography, this left bank spillway was provided on the left bank, and this is the right bank spillway. There are 40 sluices and 21 overflow spillways, and here 24 sluices and 13 overflow spans to cater for 42,400 cubics of discharge. Then, and during construction of this main dam also, Cedral Parish contributed. While finalizing the design, the extensive studies were done at Cedral Parish some 70 years back, and also structural design and geotechnical investigations are also done. And now after revising the flood from 42,452 to 69,637 assessed by Central Water Commission in 2014, it was felt that the additional spillway facility for 27,182 cubics of discharge is required. Considering the Sambalpur city, just 15 kilometers downstream of dam, and the increased flood, it was decided that one of the additional spillway to the tune of 9,122 would be provided on the left bank, and remaining discharge for 13,571 will be taken up in the phase 2. In the phase 1, the construction for phase 1 is continued, and Cedral Parish is involved again in finalizing the design for this additional spillway. Considering this existing dike here, considering as the coffer dam, the design of additional spillway has been considered so that during construction we need not deplete the reservoir level, so that it will act like a coffer dam, and the design of this will be finalized from the model studies. And there is no spill channel here. There is a hill there. Cutting of hill is required about 1.8 kilometer, and it is having a spillway to accommodate 5 spans of size 15 meter by 15 meter height, and so that design flood of 9,122 can be passed, and remaining a spill channel of about beyond about 758 meter will be the channel of 120 meter, and remaining channel will be increased to 200 meter with a slope of 1 in 3,000, and it will join to the main river here, the left bank channel. And there are so many issues. When studies were referred to Cedral Parish, so the scope of the studies were left to Cedral Parish to decide. Then when we visited the site, we found that in addition to the 2D sectional model studies, there is also a necessity of 3D model studies, as the flow from the additional spillway is impinging at right angles to the already existing left bank Mahanadi limb. So that, and also to protect the island, as well as there is a existing township here, and the height of the river embankment here is also needed, so that it's possible only after reproducing this topography and also the confluence of right bank limb, left bank being, and so that though we are not going to reproduce the right bank spillway, but we can simulate indirectly based on the tailwater levels here, the total flood of the 22,000 plus the additional 9,100 can be accommodated, so that the design of additional spillway maintaining the tailwater level in the section model just downstream of filling basin, and also the maintaining the tailwater level when the flows are released from left bank spillway and the additional spillway. And also there was a requirement of tailwater rating curve to develop the flow simulations released from the left bank, right bank, as well as the additional spillway. So this is the proposed additional spillway. This is the upstream elevation having 5 spans of 203 meter long and 33 meter high with a stilling basin, and with a slopes recovery we will have a channel of 1756 kilometers. And initially 2D section models were taken up on a 1/140 scale, reproducing 1 full span and 2 half spans, so that the profile of the spillway, performance of stilling basin, height of training walls can be decided, and also the discharging capacity. And this is the tailwater rating curve used for conducting the model studies. And through the model studies, it was revealed that the discharging capacity is quite adequate, as we are able to pass at MWL 10,257 cubics of discharge as against the design discharge of 9122. Since it is a additional spillway, the BIS recommendation of 10% gate opening in operative need not be considered, because this is not a principal spillway, this is the auxiliary spillway. And these are the flow conditions over the spillway and in the stilling basin and the downstream channel for 100% design discharge and 50% of design discharge for ungated and gated spillway. These are the water surface profiles. Normally, these are used for checking the elevation of Trunnion beam of radial gates, so that it should be adequately above the water surface profile, and also the top elevation of the training wall, which is provided at 177.5 meter. This is normally checked for maximum discharge. And also considering the bulking of flow in the prototype due to air entrainment, that has to be considered, and the freeboard requirement. The designer has to consider these 2 aspects while finalizing this top elevation. These were lower discharges. And the adequacy of spillway profile and stilling basin with upper structures of dentated and seal and chute blocks were tested by providing the piezometers all along the spillway and stilling basin. It was found that especially these pressures are investigated for low level lower pressures, so that the spillway is adequately protected against cavitation damages. You can see here for the partial gate operation with 50%, there was a negative pressure being developed at piezometer number 8, but we found that the dimensionless constant, that is called cavitation index, was much more than the critical cavitation index of 0.2. Here the cavitation index of 0.7 was observed, signifying that the spillway profile is satisfactory considering the pressures observed on the spillway profile and stilling basin. These are for other conditions of 25%. And from this, the recommendations observed were, though the stilling basin provided was 71 meter, the length of the stilling basin was quite inadequate to contain the stilling hydraulic jump. So that we calculated, although theoretically required, we found that there is a necessity of about 90 meter long stilling basin is required to accommodate the hydraulic jump within the stilling basin. And discharging capacity was quite adequate. And subsequently, we had discussions with design engineers, and after demonstrating the performance of spillway at Cedar Paris, and it was decided to have 90 meter long stilling basin with the 151 meter floor level. But subsequently, we found that though the performance of stilling basin is quite satisfactory. Since this stilling basin width is coming in 120 meter width, and subsequently there is a cutting of hill, which amounts to about wider the 200 meter long. To economize the excavation, it was decided to have the optimum design of stilling basin such that the length also can be increased, as well as it was decided to have test the model with a lowered stilling basin at elevation 149, so that the studies are in progress now with lowered floor level. This is with stilling basin floor level at 149 meter. So the design is more or less final now, and construction of 3D model is also in progress. And here we are reproducing, this is the arrangement for model. This is the part of the reservoir we are reproducing. This is the river, and this is the left dike where the additional spillway is coming and meeting the left limb of the Mahanadi at 90 degree. And this is the island. There is a township here. And also we need to reproduce the part of the reservoir. The bathymetry survey is also being conducted to reproduce this part of the reservoir, so that the flow characteristics are properly assessed in the vicinity of all these hydraulic structures. As we have to see the combined operation of this left bank spillway as well as the additional spillway. So we have to take water from here as well as here. Earlier it was felt that is there any necessity of reproducing the bathymetry of the reservoir, but we don't know, because we have to test the additional spillway for all the scenarios: ungated operation, gated operation, the combined operation of existing spillway, and also it has two-stage spillways also there, sluices, overflow spillways, and this additional spillway. With these complexities, we have to assess all these flow scenarios also be here. Now initially, if only left bank spillway is operated, tailwater will be maintained here, and the flow conditions will be assessed here, so that we can take proper downstream protection works, so that embankment top elevation can be decided to protect this township. And also, though the part of the right bank is not reproduced, indirectly we are reproducing the flow here by simulating the tailwater levels corresponding to the total discharge released from both the existing spillways. So this is the tailwater rating curve for 300 meter downstream of confluence of additional spillway and left arm of Mahanadi, and this is the tailwater level 200 meter downstream of confluence of existing left and right bank spillway. So that all the scenarios will be tested, and so that accordingly it will be helpful in considering the rule curve for operation of additional spillway in addition to the existing spillways. So this is the part of the bathymetry survey required. Already the bathymetry survey has been taken up by Cedar Paris also. So studies being considered in 3D model are approach flow conditions, because it is on the other side of the hill. So we have to say, and there is a river, the tributary from the other side. And discharging capacity, water surface profile for entire range of discharges, performance of filling basin, considering all these scenarios, because at the end of the additional spillway at the confluence point, there is a fall of 5.2 meter. So all these topographic features are to be considered. How to consider that too? Can I open that video? That video in the folder? Yeah, it is there. This come out of it.
Mr. Bhajanti, if
Yes,
it is 2 or 3 minutes, we can proceed with this. Otherwise,
Yes, sir, it is over. It's hardly 10 seconds. Video.
okay.
Yeah, it is. I think it is. I don't know what is the problem. a very big role in fine-tuning the designers, because all these flow features, it is like the nature in miniature, reproducing all the hydraulic parameters in the vicinity of the hydraulic structures. So that's why whenever the hydraulic structures are coming, because there are some structures, they were constructed without model studies also. Later on, many studies were referred to scheduled paras. And we found that if the model studies were conducted for those projects, we would have saved many, the life of the project. Also, the many hydraulic parameters would have been finalized from the model studies. And also the timing of these model studies, also very important. The study should be taken up much before the execution of the project, because sometimes the studies come to for testing parallelly when the site the project is in construction, and also the model studies come. We will have a lot of difficulties in accommodating the modifications indicated by the model studies. So we plead that the study should be conducted much before the contractual works are awarded to the contractors, so that the project can be seen in toto for the safe considerations. Thank you very much.
Okay, thank you, Mr. Bhajanpur. Our next presenter is Mr. Dr. Akshay K. Das. He's from the state of Orissa, our host state, and he's going to give us the case study of rehabilitation of Sanamacha Khandana Dam. I hope I am pronouncing it correctly.
Sanamacha Khandana. This meaning is crying little fish. So good afternoon. This dam, Sanamacha Khandana, has been included as one of the dam for rehabilitation under DRIP. So we have taken about 26 dams in Orissa for rehabilitation. Out of that, 5 projects are major dams, 15 are medium, the rest are minor project dams. For our international delegates, I would like to mention that here in India, we tell if the irrigation ayakat is up to 2,000 hectares, we call it a minor irrigation dam. If it is more than 10,000, we call it a major irrigation dam. In between our medium irrigation projects. So this is a very small dam. So I'll go through these contents. This dam, earthen dam, this is a homogeneous earthen dam. Length is 622 meters and the spillway length is 122 meters. Although it is a very small dam of 17-meter height, it provides multiple benefits. Unlike other small projects, here apart from this ayakat of 972 hectares in Kharif, 420 hectares in Rabi, then it supplies drinking water to adjacent town, Keonjhar town, which is about 8 kilometers from this dam, and it has a population about 1.5 lakhs. It also generates 30 kilowatt of power, green power. There is a small hydel project. What happened? With this dam, there are various problems. One of the major problem is its inadequate spillway. Then another very dangerous problem is retrogradating spill channel. And other problems are leakage in hydrolator barrel and the deep gully over the left side of the area downstream of the spillway. So this is the location of Sanamacha Khandana. This is the Keonjhar town. This is the index map. This is the earthen dam. This is the spillway, and this is the parent channel. And now the spill channel joins here. But before a few years, what happened? Water has gushed through parallel to this dam, and a deep gully has been formed here. And the gully traverses from this place towards the spillway. And I will show you a picture. This gully, which is of height 30 meters, and its distance from the spillway now is only 60 meters. That's why our experts and dam safety review panel, they visited this. And what happened, I want to tell you that when this gully was formed, the field engineers, they thought that they have to avoid water pass through that gully, otherwise it may come to the spillway. So they have erected a masonry wall over the existing spillway. So this length of this wall is about 22 meters. So out of 122, 22 was constructed, and 100 meter, now only 100 meter was left for the discharge of the water. You can see from this picture, this has been constructed over this, and the way 100 meter, this one is 100 meter now. So earlier the water was flowing like this. But in the spill channel, you will find there is a drop off of 38 meters. This is the spillway and this is the spill channel. Here the parent river meets. So difference is about 38 meters. Because of the strata, soil strata, it is retrogressing fast. Here, while this project was taken up under DRIP, the first and foremost work is to review the hydrology. The earlier hydrology was based on the empirical formula. Mostly we use here Dickens formula. It was 226.4 meter cube per second. But on in the year 1984, they observed a flood of 281.8 meter cube per second, and there was a flood lift of 1.07 meter above the spillway crest, and which is 24% more than the design flood. So the design flood was reviewed, and with the latest method, the unit hydrograph method, it was derived to be 374 meter cube per second. When this flood was routed over the existing spillway of 122 meters, we found that the lake level rises to 598.62 meter against the maximum water level of 598.32 meter and a TBL of 599.85 meter. That's why the DSRP suggested to get the freeboard, required freeboard, we have to increase the parapet wall. So they have provided another height of 0.5 meter parapet wall. But the major problem was with the spill channel due to its bad geological formation. So mostly the rocks were consist of quartzites, and they are very fragmenting rocks. With the small flood, they were getting disintegrated and they were let off. So the DSRP suggested we must restrict the flow to a zone where competitive rock is available, and they found that about 70 meter will be available, so that we can restrict the width to 70 meter, and additional height can be provided both sides counterfort retaining walls. But during its construction, we found that the rock is not competent for even 70 meter, so they provided about 30 meter width, and 3 numbers of falls have been provided to take care of it. 3 falls now they have provided. This is about 5 meter, then This is about 8 meter, again 5 meter. So 3 falls have been provided. So you can see this is the construction work going on. Both sides counterfort retaining walls, and this is a concrete, this spill channel. The last year in 2018 monsoon, they have released the flood over that. Of course, this is a ungated spillway. Oh. Please see it. So one thing I want to tell that the spill channel in the revised spill channel, the flow they have taken care of for about 75% of the design flood, revised design flood. So now we have to take a risk analysis. I suggest that a risk analysis should be done for next last slide. Yes, inclusion. Okay. So in the minor irrigation projects, actually extensive survey is not done for the spill channels. So that's why this had occurred. We should take care of our other minor irrigation project like that. Thank you all.
Thank you, Dr. Das. With that, we come to the end of our 5 presentations. I think we have some 5-7 minutes if anybody would like to ask any questions to the presenters. You're welcome.
Hello. For the Stilling Basin, and why is that you are going for a submerged jump?
Float number was varying from 4 to 9 for gated spillway. For design flood, it was about 4 to 4.5. For 75%, it was 5. For 50%, it was 6. For 25%, it was 8 to 9. It was varying across the range of discharge. For gated and ungated, again it was varying. The variation was between 4 to 8 for ungated, and for ungated it was 4 to 8, like that. It was varying. Yes, but yeah, that's why baffle blocks we cannot use, because the incoming velocities were more than 15 meters per second. So we cannot go for baffle, otherwise they will get cavitated. It is submerged jump.
Yes, anybody else? Please introduce yourself before asking the question.
Hello, I am Keshav Deshmukh from NHPC Limited. I have a question for Sarita Srestha. After the GLOF event, have they revised the design flood before doing the rehabilitation measures, or the same spillway capacity has been retained? There was a GLOF event where a large amount of flood came. So have you revised your hydrological study and design flood for the spillway before going for rehabilitation measures, or the same spillway capacity has been retained?
This Chinese Institute of Academy, they have also done this flood analysis, and they have given this. They have new data for the flood and design flood also. We have considered the revised data. For the actually the spillways are the same, but we have considered new dam block 1, for this upstream part. So we have considered the new data for that. Thank you.
myself is Rizwan Ali, scientist from CWPRS. So I want to add some in this coffer dam, some factors to be considered. Here, one more important aspect should be considered, that the safety of the incomplete structure at the downstream of the coffer dam. If coffer dam fails, what will be the consequence to the safety of the incomplete structures? If you recall, in Odisha there was a disaster during 90s in Upper Indravati project. So in that extensive damages were observed due to coffer dam failure in powerhouse of the Upper Indravati project. I was associated with that study, and precious lives were lost. So many people lost their lives. So we have to consider more factors in risk associated with the failure of coffer dams.
Hello, now it works. Okay, that was the point of the paper, was the coffer dams need to be considered a dam structure and retain and have a risk associated with them. So I agree with you.
Sir, myself, Dr. Nagaraj from CSMRS. So my question is to the first speaker. Sir, is it possible to avoid the downstream coffer dam by taking the diversion tunnel, to the downstream side, much downstream side, so that we can avoid, the economic, material, as well as we can say material, everything, avoiding the construction of downstream coffer dam.
Yes, obviously so. In that case, there was a downstream tailwater that couldn't be mitigated during construction for the design, and so they had to build a downstream coffer dam to keep the tailwater from backing up into the construction area. On other sites, the gradient may be steep enough downstream, so that's not required, but in that case, the gradient was not sufficient to move the waterway. It was a fairly tight channel, and hydraulic considerations didn't exist for not having that. You can, but then it gets to be a cost comparison. Tunnel construction is quite expensive. Coffer dam construction can be quite economical, and so it's a cost trade-off that needs to be done during the early stages of the design.
Okay, one last question there.
Okay, thank you. I'm Hadush. I work for DRIP. I will stay in the coffer dam question. So for new dams, we know coffer dams are normal. But for existing dams, especially when you have 30, 40 meter high reservoir and still the water is at 20 meter or 25 meter, so how do we consider? I'm not sure about it, because we have this challenge in India also. Underwater construction is always a challenge. We have sites that we did upstream phase treatment only up to the water level because the water is still high. So they are not so effective in arresting all the problems. So I want to hear more on how you do underwater construction actually, with coffer dam or without coffer dam. Thank you.
I will start with that because Ms. Shrestha was talking about that there was 2 stages of coffer dams for the repair of the project there in Nepal. And so coffer dams are still a very important part of reconstruction. But in so many cases today, during rehabilitation of dams, we do not want to drain the reservoir because the value of the water is so high we can't avoid it. There have been, and actually there's ICOLD bulletin coming out under Committee M, probably 2 years from now, because of course it takes a while to get through ICOLD. But there is a bulletin through ICOLD on underwater construction and inspection, because the technologies have been developed significantly in the last decade or so for underwater construction. I was involved in a gate guide replacement on the Shiraro hydropower project in Nigeria a few years ago. The contractor was all hard helmet diving. It was all diving, done by diving, not remote, but diving. Worked in 115 meters of water that was basically, it was silty water, so it wasn't clear. It was completely dark, so there was no visibility. But they were able to open the trash rack, put in basically a bulkhead or a cofferdam on the existing system and drain it. But they did it all underwater, about 115 meters of head. So those are possible with hard hat. But what we're finding, and it's going to be in this iCold bulletin, there are a lot of remote robots now that are able to actually see, for one thing, and you can see it above, of course, but they can hold tools, and they can hold automatic ratchets, they can hold chisels, they can hold hammers. These robots can do a lot of that work, and I think over the next few decades we're going to see a lot more robotic kind of structures, because at Shararo the reservoir is huge. It's that power project supplies about 8% of the power for the country. So you cannot take the reservoir out of service. And so there's a lot of ways to do that now, and we're getting better at that all the time. So stay tuned for the iCold bulletin on underwater construction.
Okay, we thank everybody for their presence here and their participation and interest. I'll just request Mr. Daniel Jones for a quick 2-minute summary of the session.
All right, just quickly, we had 5 papers. All of them were different from each other's, but all of them tied into how do we build things and fix things during construction or after a problem with reconstruction. My paper talked about cofferdams and how they should be designed with a risk-based approach, and then some alternatives about the different types of methods. Mr. Kabir's paper, although he wasn't here to present it, but talked about taking limited data for a watershed, developing a flood, and then breaching a dam and causing an inundation downstream and modeling that inundation. In country, there are emergency action plans being put together for almost all the major dams, and so that kind of information is really important. The concern I've got is that in that case, I think they had about 30 years of data. That's a very short time period in the hydrologic cycle, and so I think in those cases there may need to be more than one approach. There's one approach taken here. I think comparison that is helpful. But EAPs, emergency action plans, are incredibly helpful, and they are the most cost-effective approach for reducing the population at risk for a dam. Ms. Shrestha talked about the interesting aspects in Nepal with the geologic and hydrologic hazards that exist up there. I was involved in a glove project in Kyrgyzstan a couple of years ago, and realizing that the glaciers are retreating. We've got a brand new system of water systems that exist, and we've got glacial dams that have large ice pieces in them that are melting. So glove is going to become probably more and more of an opportunity in the future. Not an opportunity, a hazard in the future. I appreciated this study in Nepal because they had 3 different events in a relatively short period of time, all 3 of which took the hydropower project out of service. So we cannot negate natural hazards. Mr. Bachanti talked about the model study and showing, and I am convinced too that model studies are very important these days. Model studies have gotten to be relatively inexpensive. Model studies 23 years ago were more expensive than they are today because of the technologies of building models. And we can get some very good information out of those model studies. So those to me are very helpful and can fine-tune a system to save money and also to ensure that the system is going to work. Dr. Kumar Das talked about the dam. I'm not even going to, you didn't try, I'm not going to try. It's not going to work. Very typical of old, smaller dams. There's not one problem, there are many problems. And the one thing that I enjoyed out of the paper was that there were problems that nobody even knew about until they actually got into the evaluation of what they're going to fix. So we have to pay attention all the time and really have a very good understanding of what's on site before we start into the development of it. The option that came out in looking through the paper talked about that they had several different opinions throughout the study. And I think that's a very valuable approach to these projects, is that one person's opinion may not be the best, but having experts come in at different parts of the design to provide their opinion on what should be done. And I think the result on that dam is a very good result with the cascading system, which, as you saw operating there, was quite a nice looking hydraulic condition. So that's my summary.
Thank you, Dr. Daniel. Now I think we'll hand over to the organizers for the balance ceremonies that they would like to conduct. Thank you, everybody.
Well, we once again thank Chair, Co-Chair, Rapporteur and all the eminent speakers for this very valuable session. And as a token of gratitude, we would like now to present a memento to all our technical presenters and the eminent panelists we have for this session. For the same, may I invite our Chairman of the session, Shri A.K. Bajaj sir, to kindly come forward and present the first memento to the Co-Chair of the session as well as the speaker, Mr. Daniel Johnson. So please. Well, thank you very much. Now may I invite the rapporteur of the session, Shri M. Ramesh Kumar sir, please. I would request our chairperson to kindly present this memento as well. Well, thank you very much. And now invite on stage Shri B.V. Mudgal ji, and I would request Shri Bajaj to present the memento again. Well, thank you very much. Now may I welcome Srimati Sarita Shrestha Madam, and I would request our chairperson to kindly present the memento. Thank you very much. Now may I invite on stage Shri M.R. Bhajantri sir, and I would request our chairperson to present the memento, please. And with that, now I invite our next presenter of the session, Dr. Akshay K. Das, and I would request our chairperson to present the memento, please. And now may I invite our co-chairman, Mr. Daniel Johnson sir, to present a memento to our chairman, Shri A.K. Bajaj ji. Now may I invite all our technical presenters and our panelists to kindly come along on the stage for a group photograph. May I request our audience to give a very big round of applause for this amazing session and our panelists and speakers on stage. Thank you. Well, ladies and gentlemen, with that, the technical session 7B comes to an end, and we will have a short tea break. Post that, we invite you to join us for the exhibition and poster session. And right after that, at 4:45, we'll have the valedictory session in the auditorium. We request you all for your presence in the auditorium for the same. Thank you very much. Have a pleasant evening ahead.